So I kind of want to go over what you have in your book as we start into electric fields and Gauss's law. Electric fields are going to be in section 1513, and we're actually going to cover that quite a bit today. Then we're going to be talking about our electric field lines 15.4. These are lines. And this is directly related to the laboratory. As this will give you your ideas on how that's going to look for your lines and where those items are. And again, we'll talk a little bit more about that today. Then 15.5 deals with electrostatic equilibrium. And we'll cover the properties. But I want you to look at this because you've got some good diagrams for this in the text. Then 1516 and 1517 or 7, 15.6 and 15.7. These are real world examples. (15.6) covers the Millikan. Let's see if I can spell it right. Oil drop experiment. And the key thing for this is where we determine the charge on an electron. That's the critical experiment for determining the charge on an electron. If you go out and Google it, or you go out and look at some other things, they'll refer to a different experiment. But this really is the first experiment that helped us determine that charge on an electron. And we talked about that last night. And this is really what you're going to be looking at for understanding why we have quantized charge, and we get that piece there. 15.7 is the discussion of the Van de Graaff generator. And how it works. And we all have our hangups. Some people, it's fingernails on a chalkboard. Mine is the clicking on the Van de Graaff generator. So Van de Graaff generators are not my friend. They're fine. Everything's okay. It's just got that creepy sound to it. And I just am not a big fan of Van de Graaff generators. They're fun to play with, but not a big fan. That's just me. 15.8, this is where you're going to get Gauss's law and flux. And I encourage you here to review the other videos. In Blackboard. Look at the diagrams. And there are some GIFs that are out there that are very helpful. And I do have those links in Blackboard to those GIFs that gives you a nice visual picture of the flux and how Gauss's law works, but I can tell you that we all have our good skills and our not so good skills. And for me, describing flux to make sure that people understand it is not one of my better skills. And it's also difficult to draw in 2 dimensions because flux is really a 3-dimensional item. And so it becomes a little odd. Now, for what you need to know and the problems you've got, I've got great examples, and I really suggest that you look at it, your example in the text. And I believe you even have this example as one of the homework problems or one of the pre-work problems was looking at example 15.7 that you're getting that example, and then you really need to look at example 15.8 because example 15.8 leads us to our first electric device. And we will come back to this in a later chapter. So that really gets us what's there, and that's what's going to complete this chapter for us. But hopefully this gives you a kind of a picture of where we're headed and what we're doing and where you can go for extra information. Again, the Van de Graaff generator section is just really fun to look at. The key part here for 15.6 is that Millikan oil drop experiment is what gets us to be quantized. So if you're looking at what you want to be reviewing and how you want to look at that and how you want to look at the various videos that I have, hopefully this will help. All right, so let's talk electric fields. Now, I'm going to go back and we're going to look at Gauss's, or not Gauss's law, we're going to look at Newton's law. And I'm going to start with the more broad Newton's law. Force is equal to our Newton's law, or Newton's constant associated with gravitation, mass 1, mass 2 over r squared. Now, if I were to take this and we're going to deal with the Earth, so this is the Earth, and we have our little ball or our little object just above the surface of the Earth, this distance here, this r, all right, this distance is, that little distance is going to be much, 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 much smaller than the radius of the Earth. In fact, if I look at the radius of the Earth, this is going to be in the weeds. And if we think about being in significant figures, we're going to be in the weeds here. So if I rewrite this, and we did this back in Physics 1, if I rewrite this and I've got my mass of the Earth, and I have the radius of the Earth squared, this becomes something else. And then we have the mass of our object. Now that's something else we said was my acceleration due to gravity. So the force that I saw is going to be in the same direction as my acceleration due to gravity. And this was going to change based on what planet I'm on, what other object I'm on, or anything else. So we could actually write our Newton's second law like this, and we used this as weight and talked about how that weight was a factor that we saw around the planet. Now, this is all well and cool because we actually used it to our advantage. And we used it to define an acceleration when we were working with problems. But in this case, because we're dealing with a particular object, we were dealing with this, and so we could actually work through this. Now, when we're dealing with classical mechanics, we're looking at motion and we're looking at how things work. But when we start dealing with electricity, we're kind of in a different realm. And we actually see that with our particular comparison. And again, I encourage you to go watch that video, that if I look at my proton, which is positive, with my electron here, and we look at the force due to the electric force is much, much, much greater than the gravitational force. In fact, inside the atom, I can disregard gravity altogether. I can calculate it, I can do it, but I will ultimately disregard it altogether inside the atom. So my atom is going to be a different kind of an area than what I have for the Earth. So when we're dealing with mechanics, we tend to stick with this kind of an idea. Well, when we're starting to build electricity and starting to look at other things, we've got to take this into a different level. So let's go back to Coulomb's law. And remember, our Coulomb's law is our force is equal to Coulomb's constant, charge 1, charge 2, over the distance between the two charges squared. All right, now, if we think about how we're going to look at charges and we look at those charges, we can bring charges in from all kinds of different areas. We can bring charges in from infinity. We can have two charges close to each other. We can do a lot of different things. So we're going to break this up, and we're going to do this a little differently. And we're going to say, let's take charge 2, and we're going to call charge 2 a test charge. And we're going to do that because what we said what we showed and what you're going to see in terms of drawing electric fields so if I have a positive charge and we're going to draw our electric field, so I'm going to get my electric field drawing here. We can think of this as being fixed. And if I have an electrical device, I can put charge on that electrical device. And that's one of the things that we showed yesterday, playing with some of the things that you're dealing with that are electrostatic. So if I have a rod, right, and I charge up my rod is going to have a charge on it. And it's going to end up creating what we call an electric field away from the rod, right? We can actually draw that electric field and we can get that. But now we want to know what happens is if I bring in a point charge or a test charge. And so here's my test charge. And one of the things we're going to assume is we're going to assume test charges are positive. So we're going to make that assumption that a test charge is positive. We want to know what's happening to this charge based on how we're going to look at that. Now, if we do that, I can get my KQ1 over R squared, but we're going to define that as an electric field. We're actually going to make a definition here, and we're going to define that as an electric field. So we can look at this test charge and electric field, so we can actually also say, hey, I can go out here and look at this, and what we're going to find is just like what we found with here. We could look at work, or we could look at potential energy, and we could define that based off of a position. And what we're going to get to tomorrow is we're going to start looking at that, and we're going to find out that I have an electrical potential, just like I have a potential energy with Earth. I have an electrical potential that I can work with my charge distribution, and look at this, and I will get this electrical, and we can actually do things with that electrical potential a lot easier than we can handle our electric fields. I can measure electrical potential. I can infer an electric field from electrical potential, but to actually measure an electric field, it's a little hard. It's not something we can do. So we can look at this a little differently, and we can actually define our, and that's what we'll do, is we'll define our electric field as our force divided by our charge, or we can have our force is equal to our charge times our electric field. So we can get that. So what's going to happen here is we can play with this a little differently, and it's going to work just like our force problems that we were seeing. So I'm going to give myself a charge, and I'm going to make this a positive 3 nanocoulomb charge. I'm going to make this a negative 2 nanocoulomb charge. And we're going to say that this distance here is 0.2. And that's 0.2 meters. And we want to know the electric field at this point. And this, we're going to say this distance R is 0.2 meters. So one of the things that we need to know is we need to know this distance. So we got to calculate that R. So that R is going to be 0.2 squared plus 0.2 squared. And we're going to take the square root of that because we're going to use Pythagorean's theorem there. And I get 0.28 meters. So I have that. But this is going to work just like the problems that we were doing yesterday. So in this case, if this is assumed to be positive, this one is going to repel, and it's going to want to go away from this charge. This one is negative, so it's going to want to come towards this charge. So the electric field at this point is going to be additive over these two charges, and we're going to get a direction because it's a vector and it's got direction and magnitude. So my electric field is equal to KQ divided by R squared. This is the magnitude of that. I got to play with these directions because I've got to work with my positives and negatives. And we know that K is 9 times 10 to the 9th. My Q here is 3 times 10 to the minus 9. And my R was 0.2 meters squared. And this is going to give me units of Newton coulombs, is what I'm going to end up with. So if I play with my factors of 10 here, 9 times my minus 9, I'm going to get 27 divided by 0.2 squared. I get 675 Newton coulombs. And this is for my +3 charge. I'm going to do the same thing for my other one. This one is going to be my 9 times 10 to the 9th, my 2 times 10 to the -9, and I've got my 0.28 squared, my +9 and my minus, so I get 18 divided by 0.28 squared. And I get something that looks like 230 nanocoulombs. That's the magnitude of my electric field. So if I look at this, we said that this one was 1, and we have this as our 230. And we have this one as our 675. So my first one, my electric field, is going to be 675 in the J direction. So I've written it out in my vector notation. Now we got to figure out this angle. And that's going to be, the angle is going to equal, actually we should be able to figure that one out because I have a triangle that this was 0.2, this is 0.2. Guess what? That's going to be a 45-degree angle. So we don't even have to, we can just get that here. We don't have to go through the arctangent to get there because we have an isosceles triangle, so we know that that's 45 degrees. So my E for the other one is going to be 230 cosine of 45 degrees in the I direction, plus 200, and this is going to be a negative because it's going in the downward direction, sine of 45 degrees in the J direction. And if we plug that in, and this is going to end up being 163 in the I direction minus 163 in the J direction. So we're going to add our two vectors together. So the electric field is going to have 163 in the I direction plus 512 in the J direction. If I want to calculate my angle, and that's going to be 72 degrees. So if I put this up here, this vector that I'm going to get is going to look something like this. And that angle is going to be 72 degrees. So if I were to put a positive charge right there, it's going to move along that line. And we can actually calculate a variety of things. So let's do that. So that's what we've got. So now we've got our electric field. Let's calculate the acceleration if our charge is a 1 nanocoulomb charge. All right, well, first of all, the force that's going to be there is going to be our charge times our electric field. So we can actually calculate that. So I'm going to have my 163 times 1. This is going to be 1.63 times 10 to the minus 7 in the I direction plus 5.2 times 10 to the minus 7 in the J direction. Now I need the mass, okay? I need the mass of that. So if I have a positive charge, I need the mass of my proton. And my proton mass (1.67 times 10 to the minus 27 kilograms). My charge on a proton is 1.60 times 10 to the minus 19 coulombs. So that's my charge. That's the other. So if I've got charge is 1.60 times 10 to the minus 19 coulombs. Is 1.67 times 10 to the minus 27 kilograms. That's going to be my factor to get my mass, but I have 1 times 10 to the minus 9 coulombs. So this is going to give me my mass in kilograms. And that gives me 1.04 times 10 to the minus 8. And I've got 1 times 10 to the minus 9. This gives me 1.04 times 10 to the minus 17 kilograms. Force is equal to mass times acceleration. So my acceleration is going to equal my force divided by my mass, which is going to equal 1 over 1.04 times 10 to the minus 17. And we calculated our force to be 1.63 times 10 to the minus 7 in the I direction plus 5.12 times 10 to the minus 7 in the J direction. At 1.04. This gives me 1.57 times 10 to the 10th in the I direction. Gives you 4.92 times 10 to the 10th in the J direction. And that's the acceleration that would be experienced by a 1 nanocoulomb charge at that point based on the two charges that we have set up here. Now, why do we care? We care because many pieces of analytical equipment put charges in electric fields and allows us to do things. And in fact, the old CRT, our old CRT computer monitors, if I put in an electron in an electric field, run it through this electric field, it was going to bounce up or bounce down, and it would highlight my phosphorescence on the back of my cathode ray tube. And that's how I could get the registers and actually see a picture. So we need to know things about acceleration of electrons because we're going to use that to our advantage as we build electronic devices. So that gives you an idea of how those types of problems work. So let's go and look at a few more electric field lines. And again, what you're going to do as part of the lab that you're working on is you have a positive charge. And now I have a negative charge here. And this would be a dipole. My line's going to go from my positive to my negative charge. And I'm going to start to get bending. And the number of lines are going to indicate my field strength. Now, if I made this a dipole where this is 2 of the positives, you're going to see these are going to kind of come in a little differently, and you're going to see these field lines change a little bit as I'm dealing with my charges and coming into those charges. Now, the field vectors are going to be a little different, and you're going to be able to get those items in here and be able to play with them. So that's what you're going to be doing with your laboratory. All right, let's talk and let's get our flux so that we can. So the idea, if I have a uniform electric field, and I'm going to draw my uniform electric field here, and I'm going to put an imaginary plane in my uniform electric field, the flux is going to equal the number of lines going through that plane. So my maximum flux is when I'm perpendicular to my plane. That's going to be my maximum flux. Now, if I have that same uniform electric field, and I put my plane in this way, guess what happens? I get 0 flux because I don't have lines going through the vertical portion of the plane. So what we have is we are going to define our electric flux. This is our electric flux. And we're defining that as the electric field with a dot product of the area of our plane. So it's the number of lines that are going through our plane. Now, I just showed you that as we tilt our plane, we're going to get a different set of lines. And so we actually look at this as the cosine of the angle as it's related to this here. So we can actually play with that, and that will give us the magnitude, our electric flux. Now, what Gauss's law says, that the electric flux through, and then this is going to be my electric flux, through any closed surface is equal to the net charge inside the surface. Or I can write it like this. And that's divided by something that we call the permittivity of free space. And it's a constant of the universe. And our permittivity of free space is equal to one over 4 pi times Coulomb's constant. And it has a value of 8.85 times 10 to the minus 12 Coulomb squared Newton meters squared. So what this means is this. So Gauss says, here's my electric field. I can put a sphere through this electric field. And if there's no net charge on the inside, the number of flux lines that go in equal the number of flux lines that go out, I have no flux. For this particular sphere, or at least at that surface. But if I have my sphere and I put in here a plus 2 nanocoulombs, and I'm going to go ahead and use black for negative, and I got one negative 3 nanocoulombs, and I got a negative 5 nanocoulombs. The net charge inside is going to equal 2 minus 3 minus 5, and this is all nanocoulombs. So I get minus 6 nanocoulombs. My flux is going to equal minus 6 times 10 to the minus 9 divided by my permittivity of free space, which we said is 8.85 times 10 to the minus 12. So my flux is going to equal this is the magnitude. Going to equal 6.78 times 10 to the second. And this was in coulombs, and this was in Coulomb squared, Newton meters squared. So I'm going to end up with Newton meters squared coulombs. And because it's a negative, my flux lines are going to be coming in this way. So the problems, while it's a odd concept to be discussing with our field lines, how it actually works for problems is pretty straightforward. Now, conceptually, if you're dealing with some of the conceptual problems, it's going to be a little bit more challenging as you're trying to think through how the charges are going to behave. For example, if I have a cylinder and I'm told that I only have flux lines coming out here, what is that telling me about my electric field inside my device? That's going to be a little bit more difficult to kind of put your head around as to how that gets in there. But that's why I have those other resources to help you out. Okay, so that gets us through this chapter. Again, I have